So our next speaker, Mike Csukai, a short name but a difficult one to pronounce, a little bit like mine, and I found out today that Mike's name, like mine, is Hungarian, so there seems to be some link between short and impronounceable names in Hungary. Mike spent 14 years in Syngenta, which is an ag-bio company, and they specialise in innovative solutions to product production. So, thanks, Mike. And this is about crop.
This is about crop protection, and I'm aware that the majority of you in the audience aren't actually working in crop protection. But I just thought I'd kick off by giving you some background into the global food security challenges that were mentioned a little bit by Ian. A little bit of background about Syngenta. Focus a little bit around the fungicide active ingredient pipeline, a number of different areas there. And if I have a bit of time, highlight some knowledge gaps that we have. And what I really want to try and focus, given that the majority of you aren't actually in the crop protection business, is to try and identify issues and gaps within our organisation that we'd like to try and solve. And many of you in farmer-focused companies may be sitting on tools and information that might actually be useful for us. Basically, we have very similar issues to the farm industry in many cases. It's just that we're trying to have deliver an effect in different organisms compared to mammals or even humans. Okay, so background. So there's increased food demand, not least because of the ever-increasing human population. So we turned over 7 billion people in the world late last year. The projections going forward into 2050 is that we might reach something like 9.3 billion. Obviously, there's larger bars, but basically the message is there'll be more of us. The other impact is because of increasing wealth in other parts of the globe. People are demanding increased amounts of meat, and that has a big knock-on effect on agriculture because to generate 1 kilo of meat, you need quite a considerable amount of vegetable product to go into your livestock. And the bottom line is that by 2050, the chances are that we're going to need to develop and deliver much more crops from the given land area we have at the moment. That's ignoring the impact of other effects like biofuel demand and other issues. There's increasing pressure on existing global farmland because of increasing urbanization. A lot of the building that goes on throughout the world is actually going onto high quality farmland. A lot of cities are in deltas, which is fantastically fertile farmland, and that's been eaten up. You're having negative impacts on soil fertility. You're having huge pressures because of the need to generate fibre, fuel, feedstocks, and fine chemicals. And not least, in biofuels, something like 40% of the US corn crop was used to generate biofuels in 2011, rather than going into food. So the bottom line is the globally farmed land is a finite amount of land. If we don't want to expand into native tropical areas, which would be ecological disasters, then we need to be able to generate more food from the existing farmland. We're seeing increasing pressure from pests, so we're getting resistance issues. We've got evolution of new pests, so soybean rusts, UG99, which is a rust which is devastating African wheat crops these days now, which broke the resistance that was bred into wheat that was being used in Africa. And not least, hopelessly unscientific pesticide legislation in the EU. We have a very politically based pesticide legislation here in the EU. It's not based on scientific points. And unlike the American one, which is much more scientifically based. But the bottom line is, because of the political situation and the increased pressures on pests, is that we need to come up with new and innovative tools to help us produce food. pressures on farming outputs, fertilizers, nitrogen prices track oil price. So on the top right, you can see that the nitrogen price basically tracks the oil price, the nitrogen price is on the bottom, oil price on the top. A huge other factor is water. Agriculture uses 70% of the world's fresh water, and already 25% of the world's rivers don't actually get to the sea because the vast majority of the water is being used for agriculture. And a classic example of this is the Aral Sea. So in the bottom right, you can see a photo of the Aral Sea in '89 compared to a photograph in 2008. And basically, that's all being used because the water was being diverted into agriculture. It's being used for irrigation. So we have currently a lot of unsustainable agricultural practices. In Central Valley in California, the parts of the Central Valley have dropped over a meter because they're taking out aquifer water that is not being replaced. And sooner or later, that aquifer is going to run out, and we're going to have some real problems generating food in what is very fertile farmland. There's huge uncertainties around climate change. We all know about these. I'm not going to go into any detail. There's huge uncertainties. But one of the things that really piqued my attention is this graph from a science paper in 2009, which plots the average temperature over the years 1900 to 2006. And 2006 is the very small blue line in the middle of the red stuff. So that was the extreme summer of 2006. So we had huge impacts on crop yield in Europe. We had something like 300,000 early deaths because of the huge heat that was found in Central Europe. And if you plot that on what is the predicted average temperature across the world, and that might be an average summer rather than an extreme summer going forward from some of the climate models. So essentially, we're likely to have some extremely negative effects from climate change. Some areas might gain, but those are likely to be far a little bit dispersed and won't make up for the fact that some of the major areas for crop production are going to be potentially negatively affected by climate change. So how do you produce more food? Well, there's three basic strategies. You can increase the intrinsic yield potential via a number of different methods. You can try and understand and mitigate abiotic stress, and a lot of this is being done by our seeds organisation within Syngenta, trying to mitigate stress, drought, heat stress, cold stress, nutrient deficiency. And thirdly, you can generate new and better crop protection technologies. It's not all about yield potentially. There are other ways to help with sustainable agriculture. You can try and reduce agricultural inputs via a number of other methods, and some of those are precision technologies. So Harper Adams are already generating little robots that go down your vineyard or your field and image weeds. And if it sees and recognises a weed, it gives it a little squirt of herbicide instead of spraying the whole field. You can trickle these things through your field. So there's a number of other technologies that are out there that might be able to help you reduce the pesticide input into the environment. And lastly, a lot of people want better tasting food, and we're trying to work on that as well. So that was the food security challenge, and it was interesting that the Maury poll suggests that nobody believes an industry person. So if you don't believe me, perhaps you can look at the work that's being produced by John Beddington and Tim Benson, who's the food security program champion here in the UK. And actually, I think their presentations are pretty scary, and coming from a kind of agricultural side. I mean, John Beddington is already talking about the perfect storm of potential impacts which could have catastrophic effects on food production. And that might be a bit alarmist, but basically food production in the future is going to be very important for humanity. So a little bit about Syngenta now. So having just presented all that information, one of the major ambitions for Syngenta is to help the world grow more with less. So trying to generate better food security in an environmentally sustainable way. And a lot of buzzwords go around, but the idea is really trying to generate sustainable intensification. There's no point in generating intensive farming going forward if it's not done in a sustainable manner. And for us, it's not just about large-scale farms. It's about the 450 million farmers who own less than a hectare. And we have real commitment in trying to do that. Our CEO was at the G8 summit in Camp David talking about how we might be able to have an impact on sub-Saharan Africa food production going forward. And some of that can be as little as generating tiny little packs of pesticide that the farmer can afford and can actually use in his field, allowing them to actually get into technology which will deliver huge increases in yield and potential food benefit for those farmers. Global market view, the global market in agri-food is about $75 billion, so it's pretty small compared to pharma, but it's still a significant market. Most of that is in crop protection, still a little bit over half. 25% is in conventional seeds, and 16% is in GM seeds. So despite the fact that Europe has decided to forego GM technology, the rest of the world is embracing it. When, and I emphasize when it delivers advantages to the farmer with a P, with an F. Sorry. Competitors, well, Syngenta's the #1 player in the market. We have a significant presence in both seeds and crop protection research, but we're pretty closely followed by Monsanto, which has a much larger presence in the seeds and traits production area, and a small amount in CP, which is essentially glyphosate, herbicide that's used with their technology. And then Bayer and DuPont are closely following. If you break down sales within Syngenta, about 77% is still in crop protection, 23% is in seeds. And Syngenta spends about $1 billion a year on R&D, and there's about 5,000 people working across the globe. And a lot of that spend is actually going into dealing with the legislation that's required in order to allow us to register products. Where are we based? Well, I come from the Gellert Hill research site, which is in Berkshire here in the UK, but we also have significant presence in Stein and RTP in North Carolina. Those are the three major research sites for Syngenta, but there are other research sites throughout the globe. And to give you an idea of our global presence, this just flags some of the field stations and other areas within the globe that Syngenta has more than 5 people working in research and development. So we really have quite a global presence. Still need to develop further in sub-Saharan Africa, but that will be coming, I'm sure. So historically we were focused in 3 businesses: crop protection, seeds, and lawn and garden. And that was all well and good, but the new strategy for Syngenta is a very crop-focused strategy. So we have a number of key crops that we're going to be working on and trying to deliver effects. And the whole idea is essentially to the farmer, with an F, doesn't care where his solution comes from. If he's got a problem with insects on his crop, he's quite happy to take a seed-based solution. He's quite happy to take a chemical solution. And instead of having these specific, selling just seeds, just crop protection, we were interested in generating a vertical solution and coming up with integrated solutions to his problem. So integrating both technology from a seeds-based point of view, a crop protection point of view, but also around machinery and services, going into areas that were adjacent to the areas that Syngenta traditionally played in. He basically wants to solve his problem. He doesn't care about the technology. Okay, I'm going to focus a little bit more in the fungicide active ingredient pipeline now. So why look for novel fungicides? Well, despite some of the GM approaches that can be focused on certain areas, we still believe within Syngenta that many of the cases you want to deliver, many of the problems that you have in fungal control are due to a whole series of complex of fungal diseases. So in wheat, for example, you've got septoria, rusts, powdery mildew that need to be controlled to have an effective control and delivery yield. And so you can have a GM approach which will very much target one fungal pathogen at a time, but getting those into market is extremely difficult. So at least for the short, medium to long term, we believe that crop protection has a place in the market. We're also interested in looking for novel modes of action, basically to help us with disease resistance management. We're very interested in trying to develop and bring to market cleaner toxicological and environmentally profiled compounds. And also, we're interested in antifungals with a broader spectrum of the existing ones. And of course, new products quite often sell better than old products, not least because they break resistance that's in the marketplace. So how do we go about this? There's a slight dichotomy in the model for what we do. So screening 300,000 compounds a year, but we're doing this in planter on the fungus, on the fungi that we're trying to control. We had a dalliance with target-based screening in the late 90s, early 2000s, and we successfully delivered nanomolar hits at the target sites, but we found that it was extremely difficult to take those nanomolar hits, and the chemists found it much more difficult to make those implanter active. So you would have these nanomolar hits that had no implanter activity, and the chemists found it much more difficult to optimize it for implanter activity than to try and take a weaker hit that is actually active on our fungus and make it into something that is more active. So typical discovery pipeline, so you're looking for activity profile, performance, typically then go into tox profile and finance, and then go into development. Because of the regulatory pressures going forward, one of the real mantras within the company is left-hand shift. So shifting those toxicological and regulatory issues to the left. So tools which would help us look at intrinsic activity between our pests and mammalian systems, that would help us get our projects in positions where you have intrinsic activity differentials is something that's very important. We have a mantra around differential biology at the moment, trying to do this as well. So those kinds of tools are of extreme interest to Syngenta at the moment. Mode of action diagnosis, I'm going to go into a little bit now. So obviously if we're screening on our pests, typically we don't know what the compound is doing, and then we have to do the mode of action determination. And the reason for that is because once you've identified the mode of action, you can do intrinsic potency measurements, structure-based design methodologies, and also it's valuable information when you're trying to look at your toxin resistance management assessment. So typically you come into a project and you ask whether you've got a known mode of action or unknown mode of action as the first step. And basically we have a range of known mode of action assays that we put the hits through to identify whether it's a known or unknown. So if it's a known mode of action, you can typically generate a structure-activity relationship information and do plant pathogen mammalian intrinsic potency assays on the target site. If it's an unknown mode of action, then the problems start. In the fungal area, we've used haploinsufficiency and overexpression-induced methods in yeast, historically to great effect. And both these methods are based on gene dosage. Simple cartoon, but essentially that if you have haploinsufficiency, you hopefully are expressing a small amount of protein of the target, and your yeast will be more sensitive. If you're overexpressing, you're producing more protein, and your yeast will be less sensitive. And we, as I said, we've used this to great effect. And the output is typically complementary, but you don't just get the target. You typically get a whole group of things, and sifting through those and identifying which is the real target within this takes time and effort. So you use data and literature to use for the targets, express the proteins, and try to look for small molecule interaction. You mutate the genes and see if you can generate resistance obviously an area that we're interested in is can we do this more efficiently via data integration? So can we use the Boone Andrews genetic interaction data, chemical interaction data to help us streamline this process? And obviously, yeast is not always active to our compounds, so we're also interested in the ability to do this kind of overexpression work in plant pathogens. So if you haven't had the answer from haploinsufficiency stuff, which we've done in about 50% of the cases, if there's sustained chemical interest, we go on to do a number of different things. So if you've got a hypothesis you can test, you can do reverse genetics in a range of different organisms. If you have no hypothesis, you can try and generate that, and typically using generating resistant mutants, which is a boon because you can help to identify the mode of action, but is potentially a problem for the project going forward, because if you can generate resistance in the lab, then resistance in the field is going to be an issue going forward potentially. We're doing a lot of work in Phytophthora infestans, and a lot of that is due to collaborations with researchers in James Hutton and Dundee University. So I just wanted to kind of flag that up there. And also you can undertake affinity-based assays to try and identify your mode of action. And one of the key things is trying to get away from models, so actually doing your mode of action discovery and a plant pathogen. And I just listed here some of the key issues and key abilities that you want to have when you're trying to develop a platform. Efficient transformation methods, good homologous combination efficiency, inducible titratable promoters, good predicted protein databases, and the ability to map resistant mutants. And we've done a lot of work in Myxophaeral graminicola, which is one of the cereal diseases in Northern Europe. There's a lot of information on this slide, but basically it's the #1 pathogen in our #1 fungicide market, so we spent a lot of time working on that. And we got ourselves into a pretty good place. We're still missing an inducible promoter, and we did a lot of this work in-house, basically because there were no academic labs working particularly hard in this area. And we actually published the data, because similarly to the pharma area, we can't do all this kind of things ourselves. Myxophaeral is a good model. Other pathogens need, particularly oomycetes, so Phytophthora infestans, that's being worked on here at Hutton, is significantly different. It's not even a fungus, for example. And so delivering those kinds of tools in a range of our key pathogens would be something that Syngenta would ideally like to see in the future. And probably that work will have to be done in academic labs. A little bit about biokinetics. So this is our name for ADME. So essentially it's following the same kinds of things that ADME is going through. So it's about uptake, stability, and metabolism in plants, in fungi, in insects. We're very interested in those kinds of things. And so we have significant gaps in these kind of areas. So the ability to follow a compound within the cell without a radioactive molecule would be one that's very much of interest to Syngenta. Range of efflux reporters in plant pathogens, equally in insects. Similarly for metabolism, we're very interested in what's going on in the plant pathogen, in the plant, in the insect. We're also interested in understanding metabolic capability in plant pathogens. And resistance assessment, we're really missing tools for better quality resistant assessment. So if you can generate a resistant mutant in the lab, that's great, but the numbers that you're generating are so tiny in comparison to what's going on in the field. We struggle to really have a proper quality assessment of what might be going on, yet it's a key problem that's thrown at us by many people. And also, what we're trying to do is be smarter about identifying biologically relevant chemical space. It's a mantra for everybody, but target-based screening is still not a popular concept in our organizations, and there's a strong focus on hypothesis-driven target starting points. including using relevant farmer targets and chemistry as starting points. So again, a touch point within with what's going on in pharma. And I think I've used most of my time, so I'm going to skip through some of these because I don't really have time. I'm not massively interested. Other than to say that anybody in academia who wants to work on plant pathogens, a significant better understanding of genetics and biochemistry of plant pathogens is really, really nice. So we're hugely missing a lot of the information. And the model systems that are out there at the moment are pretty poor in comparison to predicting what's going to go on in a plant pathogen. And we're dealing with hugely diverse organisms from a bit of evolutionary scale as well. I've listed a few general areas of interest, particularly in the biological sciences. So we're interested in weed, insect and fungal resistance, including mathematical modelling, metabolism in fungi, plants, nematodes, insects, including modelling and prediction, predictive toxicology between pest and non-targets, chemical biology, systems and synthetic biology and agriculture. I don't think I need to read all of these things, but there's a whole range of things that have touch points with the farm industry that if your company or academic lab is interested in these areas, we'd be more than happy to speak with you or gather those ideas. And to that end, you know, Syngenta doesn't do all the good work in the world by no means. I mean, we're a relatively small research organisation. And to that end, we put this portal on the web recently, so you don't necessarily have to have a contact within Syngenta in the particular area that you're interested in doing some research work in, or have an idea or a potential solution. You can go to the Syngenta Thought Seeders area, you can submit an idea or proposal or collaborative idea. It would go through a triage process and be sent to the scientists within the company that will have or be particularly interested in those ideas. So I'd very much encourage you that if you have some ideas or touch points that where your companies or labs may think would be of value to Syngenta to use this, if you don't already know some good things to send the ideas to. And with that, I'm open for any questions.
Okay, thanks, Mike. Are there any questions, please?
Great talk. I thought it was very interesting that your organisation doesn't really like the target-based approach, that you do a lot of essentially phenotypic screening. I was curious, the poor track record that you had with the target-based approach, was that due to the targets being invalid or due to the properties of trying to get into the cells and into the plants?
I think most of the cases it was the translation of nanomolar hits out of targets to implanter activity. So I think it's uptake and metabolism or something along those lines. They just weren't getting to the targets in implanter. We basically have two ways of introducing compounds compared to pharma with the pH. We spray or we seed treat. And so if the physical properties of the compound mean that it doesn't get delivered to where it's required to have an active fungicidal effect, then you don't see any activity in implanter. And that's a key issue for us, and that's why a lot of the screens that we do, we don't just do in vitro, we do in implanter. We try to have the plant involved in the screen itself. So we do a lot of leaf piece assay kind of assays so that we can try and pick up those kinds of things as well.
Can I ask a quick one, Mike? So given that something like 700 different compounds are due to be withdrawn on an international scale for use in crop protection, herbicides, pesticides, fungicides, and if it's not based on scientific common sense, then what effect is it going to have and what are we going to do about it?
Well, I mean, potentially, it was going to have a huge potential impact on food, the ability to generate food here in Europe. And already Europe is importing more and more dependent on external food production, essentially. The big issue is when you withdraw certain compounds from the market, then your whole resistance management strategy has problems. And quite often, as I said, it's very much based on political decision making rather than scientific decision making. If you put all of the compounds that have been introduced in the last 20 years by their acute toxicology, and then put paracetamol in that graph. Paracetamol is by far and away the most toxic compound that has been, compared to any pesticide. Yet most people are quite happy to pop 4 grams of that a day for several days when they have a cold, whereas they're not interested in having, parts per billion in their food. So it's about emotion and politics rather than scientific-based decision making, unfortunately.
Okay, there are no more questions. That's a nice place to finish, and we seem to have another coffee break.